All right, let's dive right into the world of gases. Now, most of us probably remember learning a really simple, neat little law back in school that was supposed to explain how they work. But here's the thing. In the real world, gases are a lot messier. They don't really follow those simple rules. So today, we're going to go beyond that perfect, ideal model and get into the fascinating reality of how gases actually behave. So here's what we've got on tap. We're going to start by busting the myth of the ideal gas. Then we'll explore the messy reality of what's really going on between molecules. We'll see how scientists figured out how to measure that messiness, and then check out the brilliant equation that actually fixes the problem. And finally, we'll see how all of this helps us understand how gases turn into liquids, and even points to a universal rule for all gases. Ah, yeah, you probably recognize this one, the ideal gas law. It's so elegant, so simple, and look, for a lot of basic calculations, it does the job just fine. But here's the kicker. For real gases, under a whole lot of real-world conditions, this beautiful little equation is just wrong. So why is it wrong? I mean, what's the big deal? Well, that brings us right to our first stop, the ideal gas myth. See, the problem is that this whole law is built on two big assumptions that, when you really think about them, are just physically impossible. Okay, so the ideal gas law basically pretends that gas molecules are these tiny, zero-volume dots just bouncing around in space, completely ignoring each other. But come on, we know that's not right. In reality, molecules are made of atoms. They absolutely take up space, and they are constantly interacting with each other, pulling and pushing with these really powerful intermolecular forces. Right, so to really get why the ideal gas law breaks down, we have to get a handle on those forces. And this is where it gets super interesting, because the way two molecules interact isn't just a simple on or off switch. It's way more nuanced than that. You can almost think of molecules like little magnets. When they're really far apart, they don't even know the other one is there. No interaction at all. As you bring them a little closer, this gentle attractive force starts to kick in, kind of pulling them toward each other. But, and this is key, if you try to shove them right on top of one another, a super powerful repulsive force takes over and pushes them apart. It's this constant dance of push and pull that the ideal gas law just completely ignores. Okay, so we've established that real gases aren't ideal. But the next logical question is, well, how not ideal are they? Scientists needed a way to measure this deviation, to put a number on it. And that led them to develop a really clever tool for quantifying this imperfection. And that tool is called the compression factor, which we just call Z. It's actually a pretty simple ratio. All you do is take the volume a real gas actually occupies and divide it by the volume an ideal gas should occupy under those exact same conditions. It's basically our yardstick for measuring just how far from perfect a gas is behaving. So what does Z actually tell us? Well, if Z is bigger than 1, it means the repulsive forces are winning that tug of war. The molecules are actively pushing each other away, forcing the gas to take up more space than an ideal gas would. This actually makes the gas harder to squeeze. It's less compressible. Now, on the flip side, if Z is less than 1, you know the attractive forces are in charge. The molecules are pulling on each other, drawing the whole gas into a smaller volume than the ideal law would predict. And that makes the gas easier to squeeze, it's more compressible. And, of course, what if Z equals exactly 1? Well, that's the magic number. It means we've found the perfect conditions of temperature and pressure, where the push and the pull, the repulsive and attractive forces, have perfectly canceled each other out. For that one specific moment, our real gas is behaving just like the perfect ideal model. You know, it's one thing to know a law is broken, but it's another thing entirely to fix it. And that's where the Dutch physicist Johannes van der Waals had a true stroke of genius. He came up with an equation that brilliantly corrects the ideal gas law to finally match reality. Let's actually build his equation together, piece by piece. First up, the volume problem. Since molecules have their own size, the actual space they can fly around in is a little less than the total volume of the container. So the fix is to subtract that excluded volume, which he called NB. Simple enough? Second, the pressure problem. Because molecules are attracting each other, any molecule about to hit the container wall gets a little tug backwards from its neighbors. This softens the blow and reduces the pressure. So the fix here is to add a little correction term back to the pressure to account for those attractions. And voila!
This is the final equation. If you look really close, you can see the original ideal gas law is still in there. It's just been modified. The pressure term, P, and the volume term, V, have been cleverly adjusted to reflect how things work in the real world. It's just an incredibly smart and powerful fix.
So what's the big deal? Well, this isn't just some abstract math problem. The van der Waals equation can actually predict real observable things. And maybe the most important one is the transition of a gas into a liquid.
To see how, we've got to look back at the groundbreaking work of Thomas Andrews in 1869. He painstakingly measured how the volume of CO2 changed as he cranked up the pressure at all these different temperatures. And in doing so, he gave us the first truly clear picture of how condensation actually happens.
So this is what he saw. He'd be compressing the gas, and then suddenly he'd hit a certain pressure and the very first drop of liquid would appear. Then something really weird happened. As he kept shrinking the volume, the pressure just stopped changing. It stayed constant as more and more of the gas turned into liquid. Then, once all the gas was gone, he was just left with pure liquid, and boom, the pressure would skyrocket with even the tiniest squeeze because, as we know, liquids are really hard to compress.
But Andrews found something even stranger and way more profound. He discovered that for every gas, there's a specific temperature, what we now call the critical temperature. If you go above that temperature, you can apply all the pressure you want, literally all the pressure in the universe, and the gas will never turn into a proper liquid. Instead, it becomes this weird, dense, fluid-like state where the whole distinction between gas and liquid just blurs away and ceases to exist. Now, this wild discovery of a critical point for every gas led van der Waals to one final incredible insight. He realized this pointed to a unifying principle that could connect the behavior of all real gases, no matter what they're made of. And he called it the principle of corresponding states. The core idea is that, yeah, every gas, hydrogen, CO2, whatever, has its own unique critical point. But if you measure their properties relative to that unique point, they all start to behave in almost exactly the same way. It's like he found a universal translator for gas behavior. So how does this translation work? Well, we just define a new set of reduced properties. You get the reduced pressure by taking the actual pressure and just dividing it by that gas's unique critical pressure. You do the exact same thing for temperature and volume. This incredibly clever trick essentially rescales the properties of any gas you can imagine onto one single universal chart. And this is the amazing result. It means that if you take any two different gases and you adjust them so they're at the same reduced temperature and the same reduced pressure, they will, in fact, occupy the same reduced volume. It's a universal law that just emerges from all that messy reality of molecular forces. And that leaves us with one last really big thought to chew on. What this principle is suggesting is, yes, it's actually possible. By understanding that one unique fingerprint of a substance, its critical point, we might be able to use a single framework to predict the behavior of any real gas, anywhere. It's just a stunning piece of science, finding that kind of profound simplicity hiding in all that complexity.